Okay, so I just got back from my bike ride. It's kind of fun. Went out to Central Saanich, um, and yeah, it's a nice night tonight. Anyway, we left off with this sort of question, which was that if we're at V half, and that is half the volume of base required to neutralize the acid, what can we say about H buff and buff minus? Well, if this is a titration curve and you're at V half, then you should have neutralized half of the acid that was available. So our buffer, H buff, is part acid, part base. And if we want this kind of sweet spot right here, right in the middle of the curve at V half, then the concentration of the buffer, H buff, sorry, and the concentration of buff minus should be the same. And that's something we learned in previous videos. And so we would say that the H buff concentration and the buff minus concentration should be equal because if you neutralize half of the acid, then you would have now half of the acid gone. So imagine this was at 1 molar, and I said before you neutralize it, the buff minus is 0. And then at V half, you neutralize half of H buff, which means this would be 0.5, and that means you would have made 0.5 buff minus. So the V half is a useful tool because it helps us find the Ka, or the concentration of hydronium, because if those numbers are the same, they would cancel from the equation, and that would give us Ka equaling the concentration of the hydronium. And that would be for a buffer that's at the V half location. Which is really analogous to indicators. Indicators have two colors, usually. I mean, it could be, I guess, colorless and in another color. And what happens then as it transitions or reaches its endpoint, it's right in the middle of the color change. And so the acid form of the indicator equals the base form of the indicator. Just as in this case, the buffer's acid form equals the buffer's base form. So we get a Ka equal to the hydronium concentration in that. So why would this be useful? Like when would you want to use this? Well, anytime that you want to maintain the pH, keep it at a constant level or really close to a constant level, you should wind up using a buffer. And so we can have different types of buffer systems. There's bacteria, for example, that live in very acidic conditions. And so maybe we wouldn't want the pH for those bacteria to be at 7. That might kill them. So we could try to maintain the pH at around 3 or maybe 2, depending on what environment is best for those bacteria. And conversely, we could have something that works better at a more basic level. And so we might want the pH to be maybe 8 or 9 or something like that. So we're going to go through some examples here, talking about how you can prepare a buffered solution. So let's pick a pretty generic buffer system, and let's say we want the pH to be acidic. We want an acidic buffer to maintain it at some acidic range. We'll keep it pretty open-ended here. Normally, you would want a pretty narrow window. For example, we talked about enzymes earlier in the course, how they speed up rates of reaction. And we know that temperature affects enzymes, but another thing that affects enzymes is pH, actually. Most enzymes are proteins, and proteins can be denatured depending on the pH of the solution. So all the proteins in your body that act as enzymes, they need to be maintained at a fairly constant pH in order for the active site to have a proper binding capacity with the substrate that it's interacting with. So let's take a look at an acidic buffer here. So our solution would have an acidic form of the buffer. So let's say H buff. And it reacts with water. And that would form its conjugate base, buff minus, just like we had above, and our hydronium. Okay, now I'm going to pick a specific chemical that would do this for us, and then we can talk about how you would know which chemical would be a better choice for you. So I'm going to pick a chemical that I know does form an acidic buffer, that means a pH below 7. And that would be if I took, say, 1 molar HF and 1 molar sodium fluoride, say. Okay, so I'm going to replace my buffer here with these chemicals. So I'm going to say I have my acid form, which is HF, and I have my base form. Now, what I'll notice here is that the sodium fluoride, I'm not sure why I put a minus there, sorry. The sodium fluoride, it dissociates into its constituent ions, which would be sodium. And we know sodium is a spectator ion, and fluoride. What's fluoride in water? Well, fluoride is a weak base, actually, if you look at your data table. So that would be our basic form here. And so we can see that a buffer has to have a weak acid and its conjugate base. So weak acid and its weak base, and maybe and conjugate base. If it's a weak acid, its conjugate base has to be a weak base. Okay, so let's take a look then. So we take a look at water is just water. So I'll just put H2O in back in the equation. And let's say someone said, okay, well, fair enough. You make this buffer solution. It's got some fluoride ions. So those ions could act as a base if you were to add acid. And you've got HF, which is obviously an acid. But what would this buffer add? Like what would be the, I guess, the outcome of this buffer here? Well, notice that I made the concentrations 1 molar and 1 molar. So basically, you've got a molar, 1 mole per liter of acid, and you got 1 mole per liter of base, which is the fluoride. And so if you were to throw an acid at this or a base at this, it should be able to maintain the pH, whatever that pH is. But notice I use 1 molar, which is actually quite high. If you had maybe made it like, say, 0.001 molar and 0.001 molar, that actually would also work as a buffer, but it wouldn't be as good as a 1 molar buffer solution, because you just have more moles of acid and base to neutralize more of the acid and base you add to the solution. So anyway, so what would the pH of this buffer be here? So you make this, maybe it's I don't know, you're growing it on you're going to put it on a petri dish and maybe see if some bacteria can colonize it. And so you would make this buffer and you would put it into the agar solution. And I'm pretty sure this would not be a good choice of buffer for that, but you know, I mean, maybe you're just wild and crazy, you want to try that. So what would the pH be here? Well, the Ka for this expression would be the concentration of the fluoride multiplied by the hydronium and divided by the conjugate acid, HF. Now, the way I've made this buffer, I put in 1 molar HF and 1 molar fluoride. So these two chemicals are at a concentration that's going to be at V half. So basically this would wind up being Ka at V half. So if we're at V half, the concentration of the acid HF is equal to the concentration of the fluoride ions, F minus. And if that's the case, then the fluoride and the HF should cancel, which means for this particular buffer, if you made it this way, that means you start 1 molar, then the Ka should be equal to the hydronium concentration, or the hydronium concentration should be equal to the Ka of this acid. So this acid has a Ka value, I believe it's 3.5 times 10 to the minus 4. And I'm just going to check out what kind of nerd I am here. 3.5 times 10 to the minus 4. So Mr. Dixon is an uber nerd. So some numbers I just sort of have memorized now. Okay, so that's your concentration of your hydronium that would be in the solution that I just prepared here. And what would the pH be then? So the pH of this buffered solution would be the negative log of the hydronium, or negative log of the Ka, actually, which is interesting. So I'll say negative log of the hydronium But more specifically, if I make a buffer where the acid and the base are equal concentrations, it's the negative log of the Ka of that particular acid. So the negative log of 3.5 times 10 to the minus 4. Now you can see it's minus 4 up here. So even without a calculator, I know the pH has got to be somewhere close to 4. I can work that out if I could just find my calculator. So there we go. So let's go negative log of 3.5 times 10 to the minus 4. Yeah, so I get a pH equal to 3. I guess with sig figs, 2 sig figs, so 4, 6 here. So that wouldn't be necessarily a good buffer for human skin cells to grow, or other parts of the human body. Although in the stomach, the acid environment is quite low there, or sorry, quite a low pH. But I think most of the cells are protected by a mucosal membrane surrounding them. But anyway, but there are bacteria, of course, that can colonize the stomach and cause ulcers and stuff. So they might work better at a lower pH. Okay, so there's a buffer that would be fairly low pH. So we would call it an acidic buffered compound. Now, I guess the question is, why is this a buffer? Like what makes this a buffer, like what I've just done here? And I want to go back to the curve, and I'm hoping that will make sense to us here. And so what I'm going to look at here is this curve, and I'm going to put pH on this axis, and let's just say volume of base. And I'm going to write the reaction up here. Maybe I'll scroll over a little bit. I'm going to say HF plus water, equilibrium F minus, and hydronium. Now, if you think about the curve of this, I mean, it's a big curve, I guess, right? And the question is, where would you be on this curve if you made the buffer this way? Well, I made it by having 1 molar HF and 1 molar fluoride. So I would have equal amounts of HF and F minus, which actually is the definition of V half. So where is V half on the curve I've just drawn? This curve here, where would V half be? Well, V half, so don't forget over here, that's the equivalence point. So down here, that's V. That's the volume needed to reach the equivalence point. So V half would be right there. That would be V half. And that means that if I make this particular buffer, I'm going to be right in the middle of that almost flat spot. Remember we were saying earlier it's almost flat. It does go up a little bit, but it's almost flat here. So let's say that you're growing these bacteria on this dish. We'll call them, I don't know, I won't call them anything. But let's say the bacteria, they're just doing the things that bacteria do. And they start to produce waste products, so they're growing. And some of the waste products that they produce are acidic compounds. So what would happen is the agar solution, agar compound, the pH of that would start to go down. And if it goes down too much, then the bacteria, they won't be able to grow on the dish because the conditions are just not favorable for them to grow. But the agar dish, with its buffer, and so once again, let's say the bacteria, they're producing acid. This is a biological waste of the chemicals that it can make. And what you would notice is that if you start making H pluses, the concentration of the hydronium would go up because you're making H pluses, the bacteria making H pluses, and that would cause the reaction to shift, according to Le Chatelier. If you increase that, it would shift that way. And so you would go up, and then it would start to go down a little bit. Now, as it shifts that way, it does make more of the HF, and it would use up some of the F minus, not necessarily all of it. And what would happen is it would start to move that way on the curve. And if the bacteria were allowed to keep doing what they were doing, and then they would just keep making more H plus, and the reaction would just keep shifting more and more to that side, and it would just keep going more in to the left here. Now notice that that line is pretty much flat, so the bacteria would be fine even though they're producing all this H plus, and without the buffer, that would actually cause the pH to become so low that it would kill them. But right now, they're actually doing quite well because this solution has this buffer built into it. Now, if for some reason you accidentally spilt some hydroxide onto this thing, and you started to make the concentration of hydroxide increase, well, the hydroxides would neutralize the hydronium, so they would drop the concentration of hydronium. And of course, if you lower the concentration of hydronium, that's an equilibrium reaction, then you're going to shift to make more of the hydronium and more of the fluoride ions. So the hydronium would go down, 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 and then it would start to go back up again. But remember when we said in Le Chatelier's principles, if it goes down and goes back up, it never goes back to its original starting point. So what would happen is the pH would start to climb again, climb and climb, be very, very gradual. But it would go up. Like, so buffers don't stop pH changes, they just reduced how drastic they can be. And of course, the buffer would just keep increasing if you kept doing this, kept adding hydroxides. And if you added some more acid, then what would happen is it would go back down, And as long as you keep the buffer in this sort of, I guess, happy zone or buffered zone, then the solution should stay pretty close to that pH of, in this case, about 3.5 roughly. Now, if you were to keep adding hydroxide, though, you just kept pouring it and pouring it and pouring it in, it would overshoot the capacity of the buffer, and it would start to go way up then. And when that happens, the cells wouldn't be able to live anymore. It would be too dangerous. Some bacteria can hibernate, so to speak. They can cause cysts to form around themselves if the conditions aren't favorable. So maybe these bacteria have that capability, but most likely I would expect the colony to be pretty much wiped out at this point. Now, the other thing about buffers is that the effectiveness of them depends on the amount of chemical you have. So for example, if instead of 1 molar, let's say you start it with 0.01 molar, 0.01 molar, the buffer would still have this range. It'd be this range of values that it would be pretty consistent between, but that particular buffer wouldn't be as good as withstanding effects to the pH and pOH, because there's just not as much chemical to deal with here. So really, if you're adding an acid to a buffer system, it's the amount of base that controls how well the buffer can handle that change. And if you're adding an acid, so if you're adding a base to a basic compound to the buffer, then it would be the amount of acid that would control how well the buffer can resist that change in pH here. Okay, so I'm going to see if we can do one on our own here. I'm going to need to pause the video here, and you'll need your data table. And let's see if you can figure out which buffer. I'm just going to do a quick calculation here. Yeah, which buffer do you think you could pick here that would maintain the pH like a pretty almost neutral buffer solution? So I'm going to choose, it's not perfectly neutral, but let's say you were trying really hard and you want your buffer to buffer around 7.2. So you want the pH to be about 7.2 approximately. You may not be able to get exactly there, but I want you to pause the video and see if you could figure out which chemicals you should use to do that. I'll write the question down. Okay, so if we're going to make a buffer, the idea is to get to this nice sort of V-half location, which means that the concentration of the weak acid should equal the concentration of the weak base, which means that the Ka expression is equal to the concentration of the hydronium ions. But I guess, it would have come from the equation of the base times the hydronium all over the concentration of the acid. So what would be a good choice here? Well, if we want this to be true, if we want this part to be true, then really we just want to know the hydronium concentration at that Ka. And of course, what we really want is we want the pH to be 7.2. That is ideally what we want to have happen. So what I could do is take the antilog of that number. So if I take the antilog, that would give me the concentration of hydronium that I want. So that would be 10 to the negative 7.20. So if I do that, 10 raised to the negative 7.2, so I'm going to switch over to scientific mode here. So that gives me a value of about 6.3 multiplied by 10 to the minus 8. 10 to the minus 8 here. See? So what chemical should I use then? Well, if I want the hydronium concentration to be 6.3 times 10 to the minus 8, then ideally what I'd want to do is pick a chemical that has a Ka value close to that value. And if I get a number close to 6.3 times 10 to the minus 8, Bob's your uncle, you should be able to find the acid that you want here. So looking at the data table, I can see H2PO4. Yeah, H2PO4. And HPO4 2 minus, that's the conjugate base. Those two chemicals have a Ka value of 6.2 times 10 to the minus 8. So it's not perfect. I mean, it's not going to be exactly that. But how would I write this up? Well, first of all, I need to use a weak acid and a weak base. So I've got both those. And I also need to use relatively high concentrations of the chemicals, so they're reasonably effective. So I could say something like mix, 1 molar. Now I need to use H2PO4. Now see how that's an ion? You can't just, there's no chemist out there that has like a bag of ions that you just reach into and pull them out. So you might want to pair these ions with a cation that has a high solubility with this. So we know that alkali ions are soluble with everything. So I might choose potassium, H2PO4, and maybe 1 molar sodium, HPO4 2, or HPO4, sorry, so Na2 HPO4. And if I do that, I've used quite high concentrations, and so I would think this buffer is going to be pretty capable of resisting drastic pH changes. And I've got a conjugate acid and a conjugate base, and I know that this would be, now this would buffer at, if I negative log that number, so if I negative log 6.2 times 10 to the minus 8. So it's actually going to give me a pH around 7.21. So, that's pretty close. It's not exactly like way out here. But, if you needed it to be 7.20, then what you can actually do is adjust the amount of the acid and base, actually. And you don't need to know this for the test, but if you're going into biochemistry and taking chemistry university, this formula I'm going to show you is called the Henderson-Hasselbalch, I think it's called. Not sure how to spell that. Hasselbalch. It's a German name. Equation. And this is purely for enrichment. You're not going to have to do this for the test. And what it is, the pH that you're looking for, I believe, is the pKa of the acid plus the log of the base form, concentrated base form, divided by the concentration of the acid. And that's all like in a bracket. You're logging that. And that actually will calculate out the pH that you want. So if you want 7.21, and so you can see you can tinker around with those amounts, and that would work. That would work well for you here. Okay, so that's how you make a acidic buffer, how you make a neutral buffer. And so you'll notice that for the neutral buffer, the pH needs to be around 7-ish. And so I chose a chemical that has a Ka somewhere close to the 10 to the negative 8. But really 10 to the negative 7 would have been perfect. But I mean, I guess if I really wanted 7.0, I might have chosen, what is the chemical there? Hydrogen sulfide ion, that might have been better. And of course, if you go back up here, we said pH 3.46, that was an acidic buffer. So let's make a basic buffer solution, and let me think here. I need to just work out a quick value. So let's say you're wanting the pH of your basic buffer. So let's do a basic buffer solution. So we want something over 7, but let's be a bit more specific. I mean, the difference between pH 8 and pH 13, that is a huge difference in hydroxide amount, and obviously quite different for different cells stuff. And so let's take a look at a pH equal to about 10.25. Okay, so let's say you want the pH to be around 10.25. So once again, you could pause the video here and see what you think we should choose for a chemical here. Okay, so I know for any buffered system, as long as I make the concentration of the acid and base the same, the Ka should simply be equal to the hydronium concentration of my solution. And of course, if I want the pH to be 10.25, well, then I obviously want the hydronium to be at that concentration. So if we want to find that out, we would take the antilog of the pH, and that would give me 10 raised to the negative 10.25. So we get 5.6 times 10 to the minus 11. And once again, you can sort of see, I'm hoping you can see here the correlation between the Ka value, at least the power on that 10, and the pH that you want. So we want 10.25. So we're wanting a pH with a negative, as a Ka value of roughly 10 to the negative 10 or 10 to the negative 11, so somewhere between there. So if I look at my data table, I kind of force this one to pop out quite nicely. And this is the Ka value for bicarbonate ions. So this actually would be if you used bicarbonate and water, we're going to get the carbonate ion forming, and we're going to get hydronium. And of course, if we look at the Ka for this thing, we get concentration of the carbonate times the hydronium all over the concentration of bicarbonate ion. Now, because we've chosen the buffer to have generally that sweet spot, what we really want to have happen is the amount of bicarbonate and the amount of carbonate, we want that to be the same amount. So they would cancel out for us here. And so the Ka value of that is 5.6 times 10 to the minus 11 here. Okay, so how would we make it? Like, what would we do? Well, once again, these are both ions. So you could say mix 1 molar sodium bicarbonate and with 1 molar sodium carbonate. So, so mixing these two together. So once I've talked about a strong acid and a strong base here, although they're in the form of a salt, which is kind of important because you have to have some way of introducing those chemicals in solution. And I also have high enough concentrations of them, which is 1 molar, 1 molar. The other compound I was going to say be careful of is that if you were to say NH4 HCO3 minus, because you might remember that ammonium is soluble with everything. The problem with that is that the ammonium itself is actually an acid. It's a weak acid. So you'd actually have a weak acid and a weak base, which probably means your pH would not really be around 10.25 here. It might be a little bit more towards the acidic side of things. But once again, I'd have to calculate that out, and we're not going to ask you to do that. So generally, we want you to show some level of your understanding of the V-half property. And then also how you would prepare it. So mixing 1 molar of those chemicals. So we'll give you some more practice on that. And I'm going to stop this video here, and we'll talk a bit about the last section here, which is on acid rain and other oxide compounds. So let me stop playing here, or stop recording here.